So what I'm going to talk about tests of general relativity from the observation of GW150914, and in particular the question I would like to address is whether astrophysical binary black holes do behave as expected, and I would like to summarize the lessons that we learned from the observation of GW15. Now, before we move to the next slide, let me just say that I am here as an ambassador, and that the work that I'm going to present, the results that I'm going to present, are based on one of the companion papers of the discovery, which is linked on the title slide, and is the result of the work of many, many people. A lot of the people are probably sitting in the audience, and I will try to highlight the contribution of the people as I go through the slides. So let's move to slide number 2. So this is the outline of my talk. So as I said, I'm going to talk about the tests of general relativity that have been performed on GW15, and in particular I'm going to spend some time describing the waveform self-consistency test that was presented in the paper, and the constraints on the parametric deviations that was also presented on the paper. Then I'm going to spend a little bit of time on things that were not tested with this particular event, but that they should be tested either in the future or on this event when the techniques and the methods and the necessary developments are available. And in particular, I'm going to spend a little bit of time on the detection of more than one quasi-normal mode in the Ringdown, on whether we can actually exclude or detect the presence of extra non-GR polarizations, and finally on the kind of constraints that we can possibly put on specific alternative theories of gravity. And finally, I'm going to conclude with the summary of my talk. So if we move to the next slide. Let me spend a few words on GW15. Now, I am pretty sure that everybody is aware of this discovery, and I'm sure that John has been spending a lot of time earlier during this conference describing what we learned about GW15. Let me just summarize a few key facts. So GW150914 did show all the expected signature from a binary black hole merger. So with reference to the figure on the right, which is taken from the discovery paper, one can, if one looks at the reconstructed template, which is given by the gray band, one can clearly identify the signature of the inspiral and the evolution of the inspiral, and finally recognize the feature of the merger and of the Ringdown. And it was particularly encouraging, and the success, if you want, already of general relativity, the fact that solutions, exact solution of Einstein's equations, are perfectly consistent with the reconstructed template. Now, from the analysis of this signal, one is able to reconstruct the masses and the component masses. One is able to extract the value of the final mass and the final spin of the remnant black hole. Now, this figure is very powerful, in my opinion, and is a very good summary of the physics of GW15, but nevertheless is not quite representative of what we actually observed in our detectors. If we move to the next slide, we see a figure which is taken from the parameter estimation companion paper, which shows how GW150914 actually appeared in the detector. Now, this figure shows the whitened strain. So if you want, the noise weighted waveform that was actually observed in the detectors. Now, the difference between the theoretical waveform, which was shown in the previous slide, and what actually was in the detector, I think is fairly evident. As you can see, the signal had just a few cycles in band that were detected above the typical excursion of the noise. Now, I'm sorry, I got distracted by the chat. So the amplitude of the waveform measured in units of the variance of the noise, which is given on the right side, right-hand side y-axis, is above 3 sigma only for just a few cycles of GW15. So, nevertheless, if we move to the next slide, thanks to the amazing techniques that were developed by the collaboration and that John has been describing earlier, those few cycles are actually enough to be able to extract a lot of information out of this signal. And in particular, one can extract information about the component masses, as I said, the final mass and final spin, but not only about this, one can get information about the distance, about the sky location, etc., and other parameters. And most importantly, which is the focus of this talk, these few cycles are actually enough to perform a test of the general relativity. So if we move on to the next slide, let's dive into the tests of general relativity that were performed with GW150914. So if we go to slide 7, before we actually start talking about the details of the various tests, I would like to spend a few minutes describing the waveform models that are used either for parameter estimation, so in the context of general relativity, and this will help clarify the meaning of the various tests I'm going to present in the rest of my talk. So, how are the waveform models that we use constructed? So the waveform models that we use are parametric waveform models, and those waveform models are parametrized in terms of the post-Newtonian coefficients and phenomenological coefficients that are calibrated on numerical relativity solutions. So as given in the equations on the slide, so the waveform in the frequency domain is as usual written as an amplitude times e to the I some phase, which depends on the frequency, and this phase is written as a sum over the post-Newtonian coefficients, which is the first term in this sum, where there is actually a typo, k should start from 0, not from 1. Apologies for that. So, so this phi k and the phi kl are the post-Newtonian coefficients, which are known theoretically by perturbatively solving Einstein equations, so expanding in terms of V over C and obtaining them theoretically, and there are various prescriptions to obtain them, plus a sum over other coefficients and other powers of the frequency that are obtained by calibration on numerical relativity waveforms. Now, the important point to take home from this is that all of these coefficients, either the ones that are known theoretically from the post-Newtonian theory or the ones that are obtained phenomenologically from calibrating on numerical relativity waveforms, for a given value of masses and spins, those coefficients have all known values in general relativity. So if we move to next slide, so how does the calibration work? So with reference to the figure on the slide here, which is just a cartoon to show the various phases of the waveform. In particular, this is showing the amplitude of a reference waveform, which is actually very similar to what we think GW15 was. So the waveform in the frequency domain is divided in various phases, which is, this division is somewhat arbitrary, nevertheless, because it's difficult to define the physical regime of transition between, for example, the in-spiral and merger and ring-down. Nevertheless, for convenience, the waveform is divided in various phases. So the low frequency, which is called in-spiral typically, which is the part that is described by the post-Newtonian theory. Then we have an intermediate regime, and then we have a higher frequency merger ring-down regime. Now, as I mentioned, the in-spiral regime is the waveform is computed with the post-Newtonian theory. This extends. The waveform extends up to intermediate frequencies, the red region. At the same time, numerical waveforms, which cannot extend to such a low frequency as the post-Newtonian theory, are computed starting from intermediate frequencies all the way down to the merger and ring down. So the intermediate regime is an overlapping regime which serves for the numerical ansatz that are chosen by the various people that construct these waveforms to find the optimal solutions that fully represent our understanding of the GR waveforms. Now, matches typically, so the overlaps between the parametric models that are so constructed and the numerical relativity waveforms tend to be better than 1%. And I am sure that tomorrow Frank is going to give far more detail than I did, a far clearer explanation than I did about the goodness of fit of our parametric models and numerical relativity. And nevertheless, in the region of the parameter space, which is appropriate for GW1509, the overlap between numerical relativity and our parametric waveform is extremely good, and therefore we can conclude that tests that are based on parametric models are valid tests of general relativity. So, if we move to the next slide, the first question that one can ask, and this is work that has been mainly proposed and led by the group there in ICTS, one can ask, okay, given the signal that we observed, is the waveform internally that we observe internally consistent? And the way one would go about answering this question is by the following consideration. So, in general relativity, the masses and the spins of the remnant, the mass and spin of the remnant black hole are determined by the initial masses and initial spins and by the orbital dynamics of the system. So one can devise a test in which one goes and compares the final mass and the final spin that is predicted from the spiral part of the waveform, so the low frequency part of the waveform, ignoring the high frequency content of the signal, and compare this with the directly measured final mass and final spin from the merging and ring down part of the signal, and then compare the two. So this is a consistency test on the waveform, and for the considerations that I did before, this is also a consistency test, therefore, on the corresponding general relativity solution. So if we look at the figures on the slide, if we look at the top one, the way in which one goes about performing this test is one consider the spiral part of the waveform, which is approximately what is on the left-hand side of the red line. This figure is just a cartoon because, as I said, the division is done in the frequency domain, while here I'm showing the time domain waveform. So from the spiral part of the waveform, one measures the component masses, and from that one can predict what the final mass and the final spin of the remnant black hole is supposed to be, and one obtains the dark pink contours in the final mass and final spin plane. Now the dark pink contour are the 90% confidence region, which is therefore predicted from the spiral part of the waveform. Then one goes about and analyzes the data considering only the high frequency content in the data, what I call the post-in-spiral or merger and ring down. And by doing the analysis, one obtains the light pink contours in the bottom panel. And if the waveform is consistent, these two contours should overlap, and in particular should overlap with the black contour, which is the final mass and final spin, which are obtained when one analyzes the data considering the full in-spiral merger ring down template. So by looking at this figure, we can see that for GW150914, the three sets of contours all overlap nicely and consistently, therefore highlighting that no evidence for discrepancies between the in-spiral part and the post-in-spiral part is detected. Now, if we move to the next slide, one can reparameterize the problem in terms of the relative difference between the measured final mass and final spin from the in-spiral and the post-in-spiral in such a way that one can actually estimate the confidence level at which the expected GR value lies. Now, in general relativity, there should be exactly no difference between the final mass and final spin that are predicted from the in-spiral and what is actually measured from the post-in-spiral part of the waveform. And therefore, the GR predicted value of 0, 0, which is indicated by a black cross on the figure on the right-hand side of the slide, is exactly at 0. Now, because of our statistical uncertainty, we have a certain uncertainty on the actual value on these parameters. And for GW150914, what we find is that general relativity lies on the isoprobability contour that encloses 28% of the posterior. And therefore, from this, one can conclude that no evidence for violations of general relativity are actually found for this particular event. Now, if we move to the next slide, one can actually go a little bit deeper and ask whether the building blocks of the waveform show any kind of deviation from general relativity. Now, as I mentioned, waveform models are described, parametrized in terms of the post-Newtonian and phenomenological coefficients. So one can go about and create a new waveform model where one allows for fractional changes in these coefficients with respect to the predicted GR value. In particular, one replaces all these various coefficients with, as given in the slide, with a new phenomenological coefficient, which is given by the expected GR coefficient times 1 plus a fractional deviation. So if one constructs such models in which these fractional deviations are allowed to be free parameters in addition to all the physical parameters of the system, one can obtain constraints on generic deviations from general relativity at all the various orders, which are summarized on the table on the right-hand side of the slide. So one can obtain constraints on all the various orders regarding the post-Newtonian series and at the different regimes of the waveform for the phenomenological coefficients. And for completeness, the table is also giving the frequency dependence, just for reference, of each one of these single coefficients. Now, if we move to the next slide, actually, how am I doing with time? Okay. Can people hear me?
Can you hear me, Walter?
Yes?
Yeah, you have about 7 minutes. And
7 minutes left?
Yeah, plus 5 minutes
okay.
for question.
Okay, so one can perform this test. So we are on slide 12. Okay, one can perform this test and obtain posterior distributions for all these parametric for all these fractional deviations from general relativity, and the plot on slide 12 summarizes what we find for GW1509. So the plot shows posterior distributions for all the different coefficients, and in the case in which they are varied one at a time, and these are given by the red posterior distributions, and in the case in which one varies multiple coefficients at the time, and those are given by the blue posterior distributions. Now, without spending too much time on the blue posterior distributions, since those coefficients are actually fairly correlated, they tend to be not very informative. Let me briefly describe what we learned out of this particular plot. So, going from left to right, we are actually looking at potential violations of general relativity at increasing frequency, and if you will, at increasing energy in the system. So, since we have very few cycles in band, and in particular we have very few in-spiral cycles in band, we can put not particularly strong constraints on the post-Newtonian series, which pertains mainly to the in-spiral regime of the waveform. Nevertheless, And this is the striking and the beauty of GW15, in my opinion. If we look at the rightmost panel on this figure, we can put very tight constraints on the merger and Ringdown coefficients, on the merger and Ringdown coefficients for GW15. So, nevertheless, all the measurements that we do are broadly consistent with what we expected from general relativity, and therefore, even from this measurement, we can conclude that no evidence for violations of general relativity have been detected. Now, if we move on to the next slide, if we look at the post-Newtonian series only, now, the constraints that we put are not particularly constraining, if you excuse my repetition, but nevertheless, the measurement that GW15 provides is the first dynamical constraint that we can put on the post-Newtonian series. And if we compare with what we could extrapolate from the variation of the orbital period of the binary pulsar, which is the system that gives us the best constraints, that gave us the best constraints to date on the value of the post-Newtonian series, we see that with the exception of the 0 PN coefficients, the improvement that we get from GW15 is orders of magnitude. Actually, this is not entirely fair comparison because there is no way for a system like the binary pulsar to be able to constrain the post-Newtonian series to the order that GW15 allows. Now, if we move to the next slide, slide 14, a further constraint that one can put, and this is the only constraint that was put directly on putative modifications of general relativity, of direct modification of general relativity. So one can put constraints on the gravitational wave propagation. And in particular, if one considers hypothetical theories where the graviton acquires mass, but in such a way that only the propagation is affected and not the two-body dynamics, and in particular the merger and Ringdown, which we actually don't know theoretically how this is supposed to be modified, one can show, and this has been shown, for instance, this has been studied in the past by Arun, has been studied in the past by Ajit there in the room, that the modification to the gravitational wave phase enters at the first post-Newtonian order and is parametrized in terms of the Compton wavelength of the gravitons. Now, by analyzing the data pertaining GW15 and letting the Compton wavelength of the graviton be a free parameter, one can put dynamical constraints on the value of the Compton wavelength of gravitons. Sorry. And what we find is that 90% confidence, the Compton wavelength of the graviton is supposed to be greater than 10 to the 13 kilometers, which would correspond to a mass of the graviton which is smaller than about 10 to the minus 22 electron volt over c squared. Now, this is not the most stringent bound to date. Most stringent bounds come from observing the dynamics of the galaxies in clusters, but nevertheless, this is the most stringent dynamical bound to date. And I would like also to mention the fact that bounds that come from galactic dynamics require a lot of modeling of the dark matter properties and content of the clusters of galaxies. Now, in the next few minutes, I would like to quickly go through the things that could not be tested and that should be tested nevertheless. So if we move on to slide 16, one of the key predictions of general relativity that could not be tested, and that I think we should work towards being able of performing such tests in the future, is, for instance, the no-error theorem. Now, if we could detect more than one Ringdown quasi-normal mode, we would be able to independently determine the remnant mass and spin. Now, this has been shown in the past in the literature, that this provides means to test the Noether theorem, and this could be done either by the detection of a golden source, so a very high signal-to-noise ratio source, but this has also been shown that combining information across multiple detections with moderate, we're talking about 20, signal-to-noise ratio, one could also perform such a test. If we move to slide 17, GW150914 was not loud enough for us to detect more than one ring-down mode. We were nevertheless able to detect a single mode, and the posterior distribution for the single mode that has been detected is shown on the slide, on the figure on the right-hand side of the slide. So we could detect one quasi-normal mode, and if one assumes that this corresponds to the least damped mode, which is n equals 0, l equal 2, m equal 2, one can conclude, one observes that the measured frequency and decay time for this mode is consistent with what is predicted from IMR waveforms. This is all we could do for GW15. If we move to slide 18, another thing that we could not test, and that is worth pursuing in the future, is the second law of black hole dynamics, or what is called the area theorem. Now, this can be paraphrased as Misner, Thorne, and Wheeler put it in their books, that when black holes collide, the sum of the surface areas of all black holes involved can never decrease. Again, to test this particular prediction of general relativity, we will need independent progenitors and remnant masses and spin measurements, and we could not do this for GW15. So, if we move to slide 19, a further prediction that we could not completely test is the polarization content in GW15. So, in general relativity, predicts the presence of only two traceless transverse polarizations. So if one could detect non-tensor polarizations, this would be a smoking gun for the presence of violations of GR. If we go to slide 20, now people have attempted, as part of the testing GR companion paper, we have attempted the detection of non-tensor modes. So in particular, by using wavelet reconstruction of the GW15 waveform using Bayes wave, what was found out is that if one assumes the presence of just the standard tensor modes, H plus and H cross, or if one compares with what is reconstructed by assuming the presence of a pure scalar, in particular the breathing mode, the waveforms that are reconstructed in a model-independent fashion are statistically indistinguishable. And therefore, it was concluded that we will need more than two detectors or an electromagnetic counterpart to be able to exclude or to detect the presence of non-GR polarizations. So if we skip slide 21 and we go directly to slide 22, I would like to summarize my talk. I think I'm running out of time. So in summary, let's go back to the title question of my talk. So, do astrophysical binary black holes, in particular GW15, behave as expected? As far as we can tell, so within our uncertainties, the answer to this question is yes. In particular, I hope I convinced you that the observed waveform is consistent with the binary black hole merger solutions in GR. And furthermore, the single ring-down mode that was observed is also consistent with what we expect from general relativity. So if we go to slide 23, however, we could not test several key predictions of general relativity, and this is work for the future. So in particular, we could not test the Noether theorem. We couldn't test the area theorem, and we could not exclude the presence of non-tensor polarizations. Now, something that I did not mention before, but that I would like to put there as food for thought, is that we could not really ascertain what the nature of the progenitors was. So, in other words, we could not prove or that the component, the two objects in the binary system that merged to form the final black hole were indeed black holes themselves. And this is also an area that deserves investigation in the future. Now, we could not impose constraints on specific alternative models of gravity, with the exception of the massive, in quotation mark, gravity model that I've been talking about. Now, the reason for which we could not perform these tests is either because GW15 was not loud enough for us to dig in the data enough to be able to do these tests, or because we do need further development, either from the theoretical point of view, for example, by the generation of numerical simulation of alternative theories of gravity, and therefore parametric waveforms that can actually be used in the data analysis, or because we actually lack the data analysis tools and methods to extract information that we need. Finally, if we go to slide 24, I would like to conclude on a positive note, because this is, at the end of the day, a new season for gravitational wave astronomy and for astrophysics in general. So we will be able to achieve more stringent limits on the gravitational dynamics by observing louder sources, and by that I mean with a higher signal-to-noise ratio, and last but not least, by observing more sources, because most of the tests that I've been showing can actually be performed across multiple sources, and the information from multiple sources can be combined for more stringent limits. And finally, given the inferred rate of the binary black hole coalescences, we should all be looking forward to a prolific season for tests of general relativity in the future. And thank you very much for your attention.
We have time for maybe one or two questions.
I don't understand your remark about the area increase theorem, because you don't need to know the progenitor details for that. All you need to know are the two black hole masses and spins. And I thought you already knew that.
Well, that's exactly what I mean by progenitors is indeed the two black hole masses and spins before they merge. But then to test the area theorem, I should be able to extract the final mass and final spin, so the physical characteristics of the remnant black hole in an independent fashion, not by using an IMR waveform, if you see what I mean. Because so I should be able to estimate the initial masses and spins without considering the constraints that come from the merger and ringdown. So if you will, by looking at the spiral only, strictly at spiral only, ignoring the information that comes from the later stages of the waveform, and then I should be able to extract the final mass and spin independently of the initial masses. Otherwise, I am not going to perform an independent test.
Any other questions? Maybe I can ask a question. So Walter, in your one of your last slides, you talked about looking for non-tensor polarizations, and so you mentioned in that context that electromagnetic observations or counterparts can help in that regard. Can you elaborate a bit exactly how that's going to be useful? For example, will you tell us about the orientation of the orbit?
Well, the way in which that would be useful is the following. So when you change the coupling between the gravitational wave signal and the detector by introducing additional polarizations or different polarizations with respect to the standard plus and cross, Now, the detector response to the other polarizations is going to be different compared to the standard plus and cross polarization. So this is reflected in the reconstructed sky position for the gravitational wave signal. So in particular, the posterior distribution in the sky is going to be will look different if you have different polarization, if you allow for different polarizations in gravitational wave signal. Therefore, if you're able to pinpoint what is the exact electromagnetic counterpart to your gravitational wave signal, you are able to exclude one of the particular possible posterior distributions in the sky, and therefore put a constraint on the polarization tensors, on the polarization content. I don't know if this was clear. So what changes is the reconstructed sky map when you have a different polarization content. So if you know where the source was in the sky, you can tell what your detector response was supposed to be, and therefore you can tell what the polarization states in the gravitational wave signals were.
Yeah, it was clear. Thanks, Walter. Let's thank Walter once again. And our next speaker is Sanjit Mitra.